Um, and this class is basically a repeat of last class lecture on Thursday, but with a different form. So on Thursday, I presented you the lambda calculus, sort of in an abstract with PowerPoints and stuff like that. And just as a refresh, this is what the syntax look like. I explained to you that these are the only syntactic rules. There's two operational rules for how to actually substitute symbols and compute in this calculus. What I'm going to do today is to actually create a programming language in front of you in Python from the Lambda calculus. So what I'm going to do is basically, this is it. What is the Lambda calculus? It's a calculus that the only thing that you have is anonymous functions. Okay, that's the one way of describing the Lambda calculus. You just have anonymous functions and nothing else. No numbers, no arithmetic operators, no loops, nothing. Just anonymous functions, nothing else. And so how can we build how can we compute basically functions with just anonymous functions, right? How can we compute the functions that we know and love with just anonymous functions? And I already hinted to you that it's by a mixture of ingenuity, a lot of interesting creative ways of using these anonymous functions, of giving meaning to these anonymous functions. And so what I'm going to do to you is to really make it come to life in the form of a Python program that implements Lambda calculus. So these are the two, just a refresher, what this means. That's basically a Lambda, and this is the application of a Lambda to something that you give it. Oops, there you go. So what do we need? First question, what do we need as a very bare minimum programming language that we know, right? So we need, this is sort of a very, very, very minimum bare bones kind of programming language that with which we could imagine. And once we have this, then we can build more things on top. So we need some sort of a void value, which is something that sort of stops the computation. Okay, that some value that is basically means nothing. Literally, it means like the nothing, the nothingness. We need multi-argument functions, which I also explained to you how to get them with anonymous functions of one argument. But then we need the stuff that we are familiar with in programming. So things like booleans and conditionals, numbers and arithmetic. We need some sort of data structures. So we start with very, very simple data structures like pairs and lists. And finally, to do something interesting with looping of some sort, we need recursion. Okay, we need some way of defining recursive functions. And once we have recursive functions, then we have the full power of iterating over things, right? Recursion is sort of the mathematical equivalence of iteration. So what I'm going to do next is show you how to build all of this from the Lambda calculus, okay? And instead of doing PowerPoint, I'm actually going to switch to REPL and just make it come to life in here. So I have a little program here hanging from the syllabus. If you care to look, there's lambda.py over here, okay, which is this program that I'm going to work with and present in today's lecture. I already have it here on the REPL. I'll just copy paste it, but I'm going to go through it so that you will see this minimum programming language kind of come to life in front of you. All right, so we need, and I'm going to use Python here, so I hope that you all can at least read Python. I know some of you are very experts in Python. I hope that everybody can at least read. And I'm going to use and abuse and overuse lambdas in Python, because that's basically what Lambda calculus is. It's anonymous functions. Lambda, the Lambda in all of the modern programming languages comes from the Lambda calculus. Okay, so basically it's functions without a name, all right? It's just functions. They don't have a name. So let's start by saying that what we call void could be something that it's a function that returns the argument. Okay, this is by definition we say this is void. So when we get something like this as a result of some computation, then we know that this is void. All right, and this is but another way that we can also define void in here in this little sort of prototype of the programming language, we can use Python itself just to say, you know, the symbol void is just to raise an exception saying that this should not be called, right? Basically, we want to get to something that stops the computation, okay, somehow, and that doesn't, it's not a function anymore, it's the nothing. So the nothing is the only thing that is not a function in here in this play example of the Lambda calculus. Hold on, just a second. All right, so let's go with this definition of void, all right? Because if we ever call void somewhere, we know that we're doing something wrong. Okay, so if I would call void, oops, sorry, then I know that this should not happen. Okay, so for those of you who are not very familiar with Python and Lambda expressions in Python, you can assign a Lambda. Basically, a Lambda it's just a function, okay? It does not have a name, but you can give it a name by means of assigning it to a name, okay? So saying, okay, this name void is this function Lambda x, returning the x, okay? Which is basically something like, you know, def void, and then you would put of x, return x, okay? So this is sort of an equivalent. The body is different, of course, because we want to raise an exception just for us to remind ourselves that we should not be calling void. This is just the beginning, it's a little weird, okay? So we have some sort of a void value that in the pure Lambda calculus would do this, but for us humans, to make sure that we know what we're doing, that we should not be calling void, we hack it in Python and just say to raise an exception, it should not be calling. Okay, these are the little bottom of the language. Okay, so the next thing that we need, as I said, is okay. Another thing that we need that I already explained is the multi-argument functions, but that one I already explained. I believe that everybody remembers how to do multi-function arguments with multi-argument functions, which is instead of defining a Lambda with 2 arguments, which you can do in Python, okay, but you cannot do in the Lambda calculus. Then the equivalent, if you constrain is if you can only have 1 argument per function, then you define a function that of 1 argument that returns another function of 1 argument, and then the body does something with both of the arguments. And so the way that you call the first function with the first argument, and then that returns the function, and then you call that function with the next argument. Right? So this is how to do multi-argument functions when your language only offers functions with 1 argument. I don't have that in my little Python here, but that is already a given because that's very simple. So next thing, so we have a void values, we have multi-argument functions out of single argument functions. Let's go to Booleans and conditions. So simple conditions are something that look like this. So if some condition is true, then you do the true clause, else you do the false clause. That's typically what we've become used to in conditionals in modern programming language. So how to do this in the Lambda calculus? So we say, so if you look at the if expression or if conditional over here, what is this? It's basically a function of 3 arguments, right? It's a function of 3 arguments. The first argument is supposed to be the condition. The second argument is supposed to be the function that you execute when the condition is true. And the third argument is the function that you execute when the condition is false, right? So basically, an if is a function of 3 arguments. and then that returns the condition applied. So you call the condition on true, and then you in the next one you call that whatever returns from that function, you call the next one. So you chain the functions. So something like this. So, but we cannot have functions of 3 arguments. We have functions of 3 arguments like this. Okay, a series of functions of 1 argument. Right. So this is in a very abstract level. Is what is a conditional? A conditional is a function of 3 arguments. Okay, the condition itself, what to do when the condition is true, and what to do when the condition is false. That's basically how you need to read this. So, but in order to have conditionals and conditions in particular, we need to have some definition of true and false, right? What is true and what is false? How do we evaluate something to true and how do we evaluate something to false? Again, this is by sort of convention, okay? So we decide that true and false are 2 sides of the same coin. And what is this coin? It's a function of 2 arguments, all right? And so you have a coin, it can be head or tail, and you decide that the true is head and the false is tail, okay? Something like that. So basically you have a function of 2 arguments, and you just say that the true returns the first argument. And false is a function of 2 arguments, and it returns the second argument. Okay, so this is basically what true and false are. So let me go now to REPL over here and basically make this come to life. So here's my if. All right, if is a symbol here in my Python program that is a function of 3 arguments, right? C, T, and F, and the body is this one. You call the function C on T, and then you call the resulting function on F, right? And then true and false are this. So let me paste this, copy paste this on the interpreter. So if I just say if, that's going to be a function. If I just say true, everything's a function, okay? Everything's a function literally in Python, as you can see, and also in the Lambda calculus. So it's a literal implementation of the Lambda calculus. So how can we do something interesting with this thing? Now we have true, false, and we have a conditional. So now I'm going to, from here on, I'm going to kind of mix a little bit the Lambda calculus with the Python instructions and statements and the Python itself. Okay, so I'm going to use the print statement of Python just to visualize things. And I'm going to even use literals in Python just to visualize things. Otherwise, it's going to be very difficult because all we have for values are lambdas, okay? And then we would have to interpret what those lambdas mean. So we can construct strings, we can construct characters out of lambdas, but then we have to remember what those mean. So in order to make it a little easier, I'm going to mix it up, using some Python primitive values to just visualize the execution of the conditional and the true and the false. So let me do this. So let's see what happens if I say print if true AAA else BBB. Okay, so this obviously is going, if our lambdas are correct, this is going to print AAA, right? And if I would say if false, it's going to print BBB. Now, this is something that you should already start getting a little curious because something is happening, right? Something is happening that is in the definition of the if, right, and the true and the false. So basically, what's happening here is the if is the way all of this expression if false AAA else BBB. This is our symbolic kind of reminder for the true meaning in Lambda, which is this thing over here. If you just unroll the symbols, and you just, oh man, this is annoying. Hello. There. If you just replace what if means by the lambda expression and what true means by its lambda expression, then you end up with this expression, right? This lambda expression, that's basically, our symbol that we are using here can be translated to the more primitive lambdas, which are this sequence of lambdas. And now it's up to figure out, by the beta reduction, right, which is actually essentially equivalent to the function called in modern languages, what is happening over here. So what's happening over here is that we have this lambda, this anonymous function over here, that's going to be applied to this first argument. This is the first argument, right? Remember, the if is a function of 3 arguments. So here's our if. And now this is the first argument that's supposed to be the condition, okay, which in this case we're using the true condition. So now we're going to replace the C with this thing over here, right? So by beta reduction, we're plugging the C to this expression over here, and etc. Now you follow the train of the lambda. So this C is going to be this guy over here, and then you're going to execute the resulting thing. You're going to bind AAA, which is the symbol, to T, all right, etc. So there you can follow manually by, in your head, the interpretation, which is the beta reduction of this expression. Okay, and this is how you are able to get AAA if the condition is true, and BBB if the condition is false. All right, is everybody following me? It gets a lot wilder than this. All right, so we have conditionals. Next, we need numbers. And in the lecture before, I explained the church numerals, which is this idea that, so what are numbers? Numbers are a function of 2 arguments. The first argument is supposed to be a function of some sort, and the second argument is supposed to be something, a thing, okay? And so what is 0 is 0 times the application of the function to the argument, which means that you just don't apply the function, you just return the argument. 1 is 1 time application of the function. 2 is 2 times application, the function, and then you apply the function again. 3 is 3, etc. Okay, etc. So if we want to define the numbers 1 by 1, we end up, with our symbolic things for us to understand, right? We humans need these 0, 1, 2, 3 symbols so that we understand. But in the pure lambda calculus, we don't have this symbolic representation. We just have these lambdas. Okay, so whenever we would see something like this, we would say, oh, this is the number 6. Okay, that's what it means. So let me go here and just paste this over here. So now we have numbers from 0 to 6. And now I have a couple of functions here, just help us for us to visualize, to convert between these lambda representation and the Python numbers themselves, so that we can know that if we have something like this, that we know, okay, is this a 6 or whatever, what it is. So we have 2 functions. We have a numeral of n that takes an integer and returns the equivalent in church numeral, so a lambda expression. Okay, let me paste it. So if I say numeral of 6, we won't be able to see it because it's going to be a function, okay? And it's going to be, just trust me, it's going to be this one over here. All right. So if you look in how numeral is defined, it's going to return the lambda of f of lambda of s, and then if n equals 0, it just returns this thing. Otherwise, it returns a function applied to recursive numeral of n minus 1, f of x. Okay, so this is a recursive function that generates the lambda, the church numerals. Okay, so, and this is, for example, okay, so this one is the opposite. N pi, what is N pi? I thought I had to remember this. Let me do what does this? Oh, I know. So not N pi is the opposite function. It's, if you say N pi of, and then I say, for example, 1, because I don't want to write that whole thing, then it just says 1. So basically N pi is the opposite. Given a church numeral, like, and I can, you know, this one, for example. Oh, sorry. I don't know what, let me copy it from here. 6. If I say N pi of this, hello, paste. N pi of this, then it's a 6. All right. So it's basically, I have two functions: numeral that takes an integer the way that we know integers and returns a church numeral representation, and we have the convert function N pi that takes a church numeral, so in the form of a lambda function, and returns the equivalent on the number that we know. Right? Okay. Everybody following me so far? These are just helper functions for us to be able to navigate this. So next, let's do some arithmetic and some functions with integers. So I presented to you before the successor function, which is this one. It's a function of 3 arguments. Basically an integer, n, which is the one that we want to find the successor. And that one returns a church numeral. That's why it has this form over here, okay? And the way that the function is going to return is one more time the application of f, all right, to that number of f's of x's. So let me do that. Let me copy paste this. So has a successor. If I say successor of, for example, 2, okay, this, if I just do this, this is going to return a lambda because there's only lambdas, okay? So if I want to see what lambda this is, I'm going to say N pi, okay, just for me to see what is this thing. So there, it's the number 3, right? It's working. How is this working? By means of this. What does successor mean? It means that you return a number, which is something that looks like this. And what that number is one more time the application of f after the application of n times f to x. Not times, I should not say times, okay, there's no times in here. The n of f of x. And n is a church numeral. That's the key here. So n is one of these lambda expressions. Okay, that's why this works. So if I say, you know, same thing for 6, I get the 7. Okay, so we have a successor function. Good. Let's be a little bit more ambitious. Let's do addition. So addition is this function over here, which I will express. Actually, let me do addition and multiplication. I'll explain both. All right, so I'm saying that addition is that function over there, which takes 2 numbers now. You see, it takes an n and an m and returns the number, right? So the way that you have to look into the lambda calculus, you have to kind of, you know, it helps to be a little high, I guess, but basically you have to look at it in a very high abstract manner. So what is an addition? It's a function of 2 numbers. You add n to m, right? So it's here are my two inputs. And what I return is a number. So how do numbers look like in the church numeral thing? They look like this. So I have to return something that looks like this. Okay, so here's my return out of those two things. It returns a number. And now what kind of number is this? It's n, and we apply n to f, and then we apply m to f of x. So basically we apply the function, the way that you need to parse this, you apply the function n times, and then you apply the function m times, and they went up with n plus m times the application of the function. All right. What is multiplication? Multiplication is similar, just the body that is different. So it takes n and an m, and it's supposed to return m times m, right? So it returns a number. So what kind of number? All right, so it's the number m, okay, applied to the number n of f of x. So basically, it's n times n, the application of f. Okay. Now this may be completely crazy, but let me show you that it works. So if I say, for example, add of 2 and 2. Okay, this is I'm sorry, what happened here? Sorry, this is wrong, obviously, because this is the wrong syntax. So I cannot do this. I can only do this. 2 and then 2, right? Syntactically, this is the correct syntax. This is a function, so I need to decode this function. So let me put n pi of this. 4. Let me just, 4, for example. Oops. So 2 plus 4, 6. Let me multiply. 8. Okay, this is working. We have addition and multiplication. We're rolling. Okay, so how can you even read this? So as I said, you have to really read this at a very high level. Okay, it's kind of hard to parse. It's very hard to parse lambda calculus. You have to kind of always remember what's the intention here. What are we trying to do? What are the types of the arguments? What's the signature of the function, and what's the return, and what's the shape of the return, right? So basically, the way that you need to read this is that both add and multiplication are functions of two arguments, so the n and the m, and they both return numbers. So if they return numbers, they return something that looks like this. A lambda of f of lambda of x. This is how all numbers look like. And then what's in here, in one case, you apply the function n times, and then you apply the function n times, which means that you end up applying n plus m times the function. And in the other case, you apply m, you apply the function m times n times of the function. So you multiply the number of applications of the function. Okay, that's why again, you can try to manually substitute to the beta reduction to see how this works. It's kind of fun. All right, so we have, let me see where we are over here. We have void values. Let me see here. Void values, we have multi-argument functions, we have booleans and conditionals, we have numbers and arithmetics. Let's add some data structures, okay? And we'll start with something very, very simple, which are pairs. What's a pair? It's just a little package of two things. And lists are, the familiar lists, which is a series of, a recursive definition of pairs, right? So what is a list? It's a pair where the first element is something and the second element is another pair, right? And so on. So that's what a list is. So let me go here. So what is a pair? A pair is very similar to it uses a very similar thing to what we've seen to true and false. So basically, a pair is has an A and a B, and an F, right? And I'm trying to remember why it has three things, and it applies F to A, and then the results to B, right? Because you always need to have a function to back things up, I guess. Okay, right. So it's it's so difficult to parse this. So basically, what's a pair? It's a function of two things. This is what you need to remember. It's a function of two things. And what does it return? It returns a function, all right? And in this particular function, it's supposed to return that the argument of that function applied to A, and then the return applied to B. So it's sort of similar to the conditional, all right? So it's sort of a structure similar to the conditional. In fact, it's exactly like the conditional. If you look at the conditional, except that we give different meanings to the conditional, and we do different things with this structure, with this pair. So in particular, what we do with pairs, just like we've learned in programming, that in abstract data types, that some sort of a type is defined by what you can do with it, right? So what can we do with a pair? We can get the left side, and we can get the right side. So we can get the first or the second one, right? So the left side of a pair, this is supposed to be the P. It's the pair applies to something that returns the first argument, and the right side of the P is the P applies to something that returns of two arguments that returns the second argument. Okay, so let me do this. Okay, so if I say, wait a minute, this is not complete. Why is this not complete? Let me go back here. There's more to it. That's right. There's a lot more to it. So, so if we say, for example, left of the pair left and right, here, we get left, and if we have right of the pair left and right, then we return that thing on the right. Okay. I don't know why I chopped this off. Maybe it was deleted by accident. I should put it back. Let me put it back. So it's always kind of going from one to the other. You know what? I'll just. All right. Oh, something happened here. Something bad. It didn't like the. Damn it. Okay, didn't like my new lines or something. Anyway, so let me go on. Once we have the pairs, then we can have lists. And as I said, lists are data structure, they're recursive pairs. That's basically what lists are. So I wish I had a whiteboard here. Let me stop sharing. Try to get a whiteboard over here. Whiteboard. All right, so for those of you who have done Lisp or Scheme, this will sound familiar, but for those of you who have never done this, this may be very foreign, but basically a list in Lambda calculus and in Scheme and in Python is something, so let's start with a pair, okay? So a pair is something that has the element on the left and the element on the right, right? This is a pair. And so what we want, a list is something that you have something here, and the next one is going to be another pair, right? And if you want to add another element, you have another pair over here. Okay? So that's the definition of a list. It's a recursive structure in here. And you can have a list that doesn't have anything. You can construct a list. You can have a predicate that tests whether the list is void or not, or that you have a list that is non-empty or not. You have a list that is empty or not. You can have the tail of a list, the head of a list. Okay, I'm going to skip this list thing. You can study it if you want. All right, and now we go to something that is really interesting, which is the recursion. So recursion, let me stop sharing the thing. And all right, back to sharing this. Let's see what I have in what survives of the REPL. Right, so you have the factorial recursive function. So in Python, if we have Python, and in Python we can have these symbols, factorial, right? So we can define a recursive, oh man, it's so annoying, can I grab the entire thing? Oh. We can define a recursive function by means of giving it a name, which is what we are doing here. Okay, so we're giving it to this, we have a lambda function over here that at some point it calls a symbol, factorial, which we happen to have defined over here. So when we have a language that gives us the possibility of having names, of naming things, then that's the way that we've learned to use to do recursion. So you have something that has a name, and then if you want to call it, you just call it with that name that you already have. Okay, but this is not lambda calculus. Okay, this is Python, and this is valid Python. In fact, you can call factorial of whatever, 5, and this works. Okay. This is valid Python, but it is not valid lambda calculus. And the reason is that in pure lambda calculus, you don't have names. You just have, so remember, everything that we are doing here, all these symbols that we are defining here on the left, are just symbols for us, mnemonics for us to remember what the hell these things on the right mean. Because our brain is not very good at looking at something like this and saying, oh, this is the number whatever for. Okay? So I have been putting all these symbols on the left so that we remember what they mean. But the symbols on the left are not lambda calculus. It's on the things on the right. The lambda expressions on the right are the ones that are the lambda calculus. So if we do that, what I just said to this function, then this is not a valid lambda calculus expression because it has this weird thing, a name, factorial. Basically, it's a free variable. This is not bound to any lambda, right? This n is bound to n, right? Even the if and the else, again, these are sort of Python-ish things, but we could even translate these things to lambda calculus because we already have that power, right? We know how to translate that to lambda calculus. So yes, they are kind of free variables over here, but we could transform them into bound variables by using what we learned above. But this factorial, comes from nowhere, right? This is something that is defined in the world of Python. It's not in the world of lambda calculus. So this is valid Python, but it's not valid lambda calculus. So how do we solve this? How can we have recursion in a world that does not have names? So intuitively, and I have a long derivation here of the lambda calculus here that you can read if you want. This, I am not going to go into detail, but basically, in order for you to understand where this comes from, you have to understand the concept of combinators. So combinators are, again, functional mathematical concepts that are functions that are supposed to work on other functions. So suppose like the arguments of these combinators are supposed to be functions. And the role of these combinators is to combine functions in some way. That's where the name comes from. So these combinators. So there are many combinators in the Lambda calculus that people have kind of cool combinators. So combinators that do really cool things. So one of them, for example, is the U combinator. So the U combinator, funky thing, is a combinator that takes a function as an argument and applies the function to itself. All right, so what is U combinator? It's a lambda that is supposed to get a function as an argument and applies the function to itself. So for example, if you define the U like this, and then you we go back here, we have the U combinator, and then you have some test function. For example, this one. And then you apply U to test. This gets to be called. Let's understand why this is called. So you basically apply test to itself. So you say, right, you say, basically this is equivalent to say test of test, right? So test of test means called because it basically, you say, it doesn't do anything with the argument, right? So whatever you send it, it basically ignores and just says called, right? So whatever you send up here, it just ignores it and it just writes called on the screen. It could be another function. If you had another function that would return, for example, X, then you would be in trouble. So if you had something like, let me see if I have that example here. Right. Or even worse, the omega combinator is the application of U to U. So the U combinator applied to U combinator. But if you had another, for example, if you had another test over here, if test was defined like this, X, and then you applied, test of test or U of test, you return it's a function, right? It's the function test itself. Okay, so this is the function test itself. Okay, so all right, let's go back here to the combinators. So basically, there's a bunch of combinators that people have come up interesting, kind of mind-boggling combinators, like U of U. If you think that it never stops. All right, so this is a second order function because it's a function that works on the combinator. All right, so we're almost, but some of these are interesting. So if you had something that you would apply the omega combinator to this functional over here, some lambda f, lambda n 1, all right? So if you'd say, for example, this, okay, let's see what happens. Oops. And so if I would say fact of 5. This is interesting. This is doing factorial, okay? So this is doing a factorial, and we never call fact on the right side. Okay, so this is an interesting middle point somewhere along of the full recursion. We have something that is a recursive function that does the right thing, factorial of the number, but it already does not need the Python name. Okay, this is a good thing towards the elimination of names for recursion. So, but on the other hand, we still call u, right? So we're still calling this u, which is defined elsewhere. So we have defined u somewhere here, or here. U is this thing over here, right? So we in this factorial definition, we were able to get rid of fact. So we're not calling fact, but somehow we're still calling a variable that is free. It's this u. This u variable is defined elsewhere. So in order for us to be able to execute this, to interpret this, we have to have defined an access or memory of what u means. And in Lambda calculus, there is no memory, right? We cannot define u anywhere. There's no memory. Everything needs to be defined within the body of the function, the Lambda expression. So we're getting there, but we're still not there. We're almost there. So let's see what the next step is. This leads us to basically to the Y combinator. Okay, so the Y combinator is this is basically what we want, that Y of f equals x such that x equals f of x. Oh my God, I'm not even going to read this. All right, let me jump here to the Y combinator. The Y combinator is a lambda that takes a functional over here and returns that, it returns this. Okay, this is what you need to do. Okay, just need to remember. So if I define the Y combinator to be this, which is still, again, it's still not completely right, and I'll tell you why, because it's still called Y, okay, over here. But let me do this middle point. You go here, define the Y combinator like this. Okay, and now if I say Y of this functional over here, right? Again, this is one that does not, it's recursive, but it does not use fact. It doesn't, in fact, I'm not even going to define fact. Okay, I'm going to define fact just to call it. If I do this. All right, so I define it like this. If I say fact of 5, does the right thing. And does the right thing in interesting ways. Again, it does not call fact. It has only bound reference, bound variables. And now we got rid of the u. So this body over here, the argument to the y, now it's complete. All the variables in here are bound. So f is bound here, and n is bound here. We're almost there. The only thing that we still have to look up is the Y combinator itself. Okay, and so this is why it's still not completely right. The way that we have defined the Y combinator, we still need to remember what Y is, and we cannot remember anything. Okay, so but we're almost there. So let's go back here and define the Y combinator in many different ways. Again, bringing back u again, but basically after going through u, let's define the best form for the Y combinator where there's no free variable. Basically, so what in here, if you look around, everything on the right side, okay, ignore the Y, everything on the right side is bound. There are no free variables. So everything that you mention on the body of this function, h, capital F, and x, is all bound here. So there's the h, there's the f, and there's the x over here. There are no free variables. That's what we want. So let's define the y to be this. Okay. And now, if we want to do the recursion of that little functional over here, right? We say y of this functional over here, where everything is bound to, right? So we can do this. All right, and now factorial 5 does the right thing. And now notice, so you may say, oh, but wait a minute, y is still here, right? So we still have to remember y. But now the problem is solved because I can just replace whatever, let me call this, in fact, I can just copy paste, okay, here's this thing. Oops, sorry, wrong keyboard. So I can just copy this, copy, I can paste it here. This is my y, all right? And then I'm going to apply it to this, which is my functional, my little function that is supposed to recurse out of the y combinator. So if I copy this and if I paste it here somewhere, all right? And then I apply this to the number 5. There. Okay, we finally got a pure lambda expression with only bound variables, no free variables, okay, that recurses. Basically, this little combinator, the y combinator, this thing, this funky, super funky thing, which is this. Let me move this back here. This is the y combinator all the way up to here. All right. This is a combinator that takes a function, a functional, it's called actually functional on the right, which is the argument, which is the thing that we know that it's going to have to recurse many times, this f somewhere in here. And basically this y combinator is capable of taking this f and generate many f's depending on the number of things that we send it. Okay, with no free variables, no names. There are no names. We have recursion without names, thanks to the Y Combinator, which is one of the most amazing things in computer science. It's basically, you have something out of no names. you can generate things purely, which is basically a generator of things, of iterations. It's a generator of iterations without having to call things by name. All right. So I'm not expecting you to understand all of the details of this. In fact, even I've studied the Lambda calculus for some time, and whenever it comes to this part over here of deriving the Lambda calculus, I still, every time that I really want to understand it, I spend like 2 hours looking at this and kind of really getting into it. So it takes, and then I always forget. It takes a sort of a lot of concentration to really get into this. Somebody is typing on the chat. I'm trying to bring the chat back, but Zoom is so annoying. So whoever typed something, I cannot get my chat window, so you may need to speak up. Sorry.
Yeah, I just had a question about the two Y combinator definitions, but I think it's fine. I got it.
Yeah. Okay. All right. So this is the Lambda calculus, and the main point that I want you to take home is the following: that you can have here an entire programming language here with just anonymous functions. Okay. I want you to really understand what I'm saying. If you have anonymous functions, you can have an entire programming language. Okay, this is really profound. I don't know about you, but I found this absolutely amazing. Okay, and what does this mean? What does this really mean? It's not just for programming. This is not just for programming. It's the fact that the Lambda calculus is a calculus that in a way it's the foundations of mathematics, right? Because, with computation, what is computation? It's the ability to compute values of functions, right? That's what it is. So what this means, all of these things that we learned in school, numbers and addition and multiplication, that we all think of it as kind of the primary base, the foundations of mathematics. What this means is that actually something even more foundational, which are anonymous functions. And if you have anonymous functions, you can construct all of mathematics on top of it. That's what it means. Okay, which is really crazy, including recursion, including the ability to recurse without having memory, without having names defined elsewhere. You can recurse, and once you can recurse, then you can do all sorts of things. What we think of as iteration and stuff can almost always be expressed as recursion. So it's really a profound, an absolutely amazing thing in computer science that everybody should at least be aware that this exists, and it kind of opens up a whole new door to looking into programming and mathematics that is quite enlightening in many ways. So basically, anonymous functions are all you need to program. Okay. Now, this is not to say that this is, programming in the Lambda calculus is kind of hard. Obviously, defining numbers like that is kind of hard, and for us, it's very low level, as low level as almost like a Turing instructions, right? Super low level, but basically, it's the foundation of everything. And this leads us to functional programming. So functional programming, and the idea of functional programming relies on the Lambda calculus. That's where it comes from, all right? So what does this mean? It really radically means that programming is evaluating functions, okay? That you give functions. What are functions? They're like mathematical functions. You give it an argument and you get a result that can be a function. In fact, in the Lambda calculus, it's always a function. There's nothing but anonymous functions. So all the values that we are used to, like numbers and strings and stuff like that, in the Lambda calculus, all of that are just Lambda expressions, basically lambdas. That's all it is. It's up to us to give some form and some shape to those lambdas to get meaning out of them, but they are just lambdas. That's all there is. And so functions that take functions and return other functions, that's the bread and butter of functional programming, because it comes from the Lambda calculus. So Lambda calculus was the inspiration for Lisp in 1960s. Lisp was literally an attempt to implement the Lambda calculus, and a pretty good one by that measure. Of course, Lisp then kind of had to catch up, and because it's so hard to program in the Lambda calculus, they added a lot of layers. Basically, at the bottom there's the Lambda expressions, but then you add lots and lots of layers that make it simply numbers and stuff like that. Everything is on top for us to be able to do the things that we are more familiar with. And in fact, Lisp was so big at some point, such a big surface of stuff and layers on top of some of the basic things that it became like a behemoth. It's too complicated, too many things. And so at some point there was an effort in the 70s, late 70s, to simplify Lisp and go back to the origins. And that was where Scheme, the language Scheme, came to light. Some of you may have heard about Scheme. It's a language that is used in many places as a kind of the first teaching language for introduction to programming in some computer science programs. But it's basically a simplification of Lisp. It's going back to the origins of Lambda calculus and going back to the simplicity of S expressions, the Lambda expressions, and removing a lot of noise that Lisp kind of ended up adding. So Scheme is a very, very simple and relatively close to the Lambda calculus.